CoppeliaSim. CoppeliaSim and uh, passive, or rather Walker simulations. Okay, the first thing is, well, so we've seen passive walkers. So let me draw the rimless wheel. And the rimless wheel is such that it's on a slope. So this is, let's say, gamma, and gravity is pointing straight down. And so gravity basically would have two components. One is G sine gamma, which is along the ramp, and then it will have G cosine gamma, which is vertically downwards, where the downward is right angles to the ramp. Now, this is how we envisage things, but what you can do is, and this we've done in MATLAB, that is, instead of having a slope which is at gamma degrees, we assume that it's on the flat ground, and instead of having gravity pointing uh, vertically down with the component g, we can instead put gravity as g cos gamma and g sine gamma. So now we can actually work with this simulation in the flat ground scenario, but just rotate gravity. So if you can set the gravity in this fashion, then we can actually do all the passive dynamic simulations on level ground, okay, which is kind of neat. So this is not a problem with MATLAB because we can do whatever we want with gravity. But then in CoppeliaSim, there is a gravity assigned to the system. And if we can tweak that gravity such that the gravity points this way, we can actually get that rimless wheel, which was, if you remember, the rimless wheel was on a boom and it went in a circle. So one way of getting it to go on a slope is to put a slope, but the other way to get this to go on a flat ground, so that you simulate the slope, is to actually have a gravity component, which is g cos gamma vertically downwards, and g sine gamma, which is along the direction of motion. So in this case, the planar case, it's very simple. If you think of this as x and this as y, then always g sine gamma is along x and g cosine gamma is along negative y. However, in this case, when things are going in a circle, CoppeliaSim, g cos gamma is always along the z components. That's not a problem. But g sine gamma now is not along the x direction because the x direction keeps changing. So if initially the x was like this, and let's say that y was like this, now the x, well, here we will have y, sorry, this will be x still, same direction, and y will still be this way. So now, in this case, g sine gamma is pointing towards the x direction, but here g sine gamma will be pointing along the negative y direction, and so that will keep happening. So basically, what we need to do here is be able to find the component of gravity in the horizontal direction, but we need to keep moving it as this rimless wheel rotates. So one way of doing that is to keep track of the angle made by this boom with the horizontal, okay? And that can be easily done if you know the position of the, let's say, base, and you know the position of a point on the robot. So let's just call that the robot. Right, and then this angle, let's call that psi. Psi is usually used for the heading. In this case, or the yaw angle, let's use that. And then you can see that if you want to find psi, that is going to be tan inverse of the y component. So if this robot was, so in CoppeliaSim, you can keep track of points, right? So if you keep track of the base and keep track of the robot coordinates, then you essentially do robot So it's the y component. So it's going to be 2 minus base 2. So that's the y component divided by the robot x component minus the base x component. So this is basically y divided by x, so something like that. Now, it turns out that if you do this, the tan inverse which you get in, if you just use tan inverse, or if you use math.a10, which is in the Lua library, then that tan inverse is not the tan inverse we seek. It basically doesn't take care of the sign of the x and y sign in the proper way. What you need to do is you need to use what is known as the a tan 2. Okay, and this is the proper inverse to use, because that basically takes care of not only the angle but also the quadrant. So it actually, the a tan 2, so a tan 2 basically goes from 0 to pi. Maybe I should put it this way: 0 here and goes to pi there, and then this way it goes in the negative direction to minus pi. Okay, and then that's good enough. So use a tan 2. So what we'll do is we'll basically do, if you want to find the gamma angle, the psi, then we'll just do math dot a tan 2 robot 2 minus base 2 divided by robot 1 minus base 1. Okay, so that basically gives me gamma, but I still need to find what is the angle made by the gravity vector with the frame, which is actually, it's rotating with the object. So if you think of the boom as moving in a circle, you have x and y, then pretty much this thing is going to move in a circle, x prime, y prime. So that's basically where the rimless wheel is at some point of time. Okay, and we want to basically find how this x prime, y prime changes with time. So what we can do is we can join this with the center. We have the psi angle, which we already found. The formula is here. And if you look at this carefully, this actually corresponds to what we've done for rotating frames. So hold on, I just did an error here. This shouldn't be, I extend the x and y. This should be, to be consistent, this should be x prime, because then you rotate it x to an angle x prime, and then this should be y prime. Okay, now it's right. This is the psi angle, and we can see that this is basically what we had done in when we rotated the frames. Okay, so we know that associated with this psi is the rotation angle given by cosine psi minus sine psi, sine psi, cosine psi. Okay, so we know that. And then remember that when we talked about the horizontal and vertical thing, we talked about g cosine gamma, which is the z component, which does not change. It's actually going to be negative. And the component along the horizontal is going to be g sine gamma. Now this g sine gamma is going to be in this direction, because it always is towards the heading. So this is going to be 0. This is going to be g sine gamma in the local coordinate frame along gamma. We need to convert that into the global coordinate frame. So we want the global x and y. This is global. Here we need to put the local x and y. Right? This is the local. This is basically the same formula I wrote down for rotating frames. So now let's just sub in the values. So cosine psi minus sine psi, sine psi, cosine psi. And then we can say the component in the x direction is 0. The component on the y direction is g sine psi. And so we can write, if you do the multiplication, gx equals 0 times cosine psi times 0, which is 0, and then minus sine times, I'm doing an error here. This should be gamma, right here. That's the slope, while this is the yaw angle. So it will be minus sine gamma, sorry, sine psi times g sine gamma. And then for gy, we would have sine, sorry, that's sine multiplied with 0, so that's 0. So cosine gamma will be that. So cosine gamma times g sine, cosine psi times g sine gamma. So that's the gx, that's the gy, and then the gz is always going to be minus g cosine gamma. Now, this is only if the rimless wheel is moving counterclockwise. If the rimless wheel is moving clockwise, again, I can draw that situation here again. X, Y. Okay, I'll still have this to be my X prime, still have this to be Y prime. Except by my G is going to be along this direction. So it will be G sine slope, is still psi. And the only difference will be that when I find the Gx, Gy, I'll have the same formula as before for the rotation part. However, now the X component is, well, it's 0, but the Y component now is along the negative Y direction. So it'll be minus G sine of gamma. And so when I do the math, it'll come out to be minus G sine gamma times minus sine psi, and then Gy equals minus G sine gamma times cosine psi. So in this formula, which is clockwise, you see that there's a negative here. And if you look at the other formula, which I wrote on the earlier page, this is clockwise, you see that there is no negative sign. The only difference happens is if you want to go counterclockwise, you need to put sorry, this is CCW, right? Yeah, this is counterclockwise. You need to put the positive sign. If you're going clockwise, you put the negative sign. Okay, and then of course GC I did not write, but it's G cosine. So what we can do is we can generalize this and write the sign like this. So we can say Gx is minus direction G sine gamma minus sine psi. Gy equals minus direction, sorry, plus direction G sine gamma cosine gamma, and then Gz equals G cosine, this should be gamma. Okay, where direction, I would set it to +1 if it is going counterclockwise. So then the formulas will be one previous page. I will set it to -1 if it's going clockwise. And so I can take care of both cases by this. The only thing I need to set here is the slope, which is gamma, and then I need to set the direction. So once I do that, it'll actually start going clockwise or counterclockwise, and gravity basically pushes it in that direction. So that's the first thing I wanted to say. The second thing is about what we've discussed in the past about how do you actually figure out the angle made by the torso with respect to the vertical. Okay, and so the trick here is, so again, the same thing, what's going here is we have a rimless wheel with a torso. And we need to find the angle made by the torso with the vertical. Okay, and so we've seen that you could use, you could use the transformation matrices, or you can use the spherical coordinates, but there's a simple way to do this with what is known as dummy variables, sorry, dummies in CoppeliaSim. So what you do is first you assign a dummy, and I'll just keep the dummy here, just in the projection of the center of the rimless wheel, and then I'll assign it a position, which in this case is just a projection, and I'll set an orientation. Okay, and that orientation, the way I set the orientation of that dummy is, again, use the same concept of the yaw, of the heading angle or the yaw angle. So if this is psi, I always set that dummy to be having its x is something like this, x, y, and z is pointing out of the plane. So this is how I set the orientation. And so if I set the position and orientation of the dummy, that's the dummy, then all I need to do is I just need to say, I think it's get orientation of the torso, where this is the torso, with respect to this dummy. In fact, I think I'll call it frame in my notes, because that's a moving frame. And then that will give me the Euler angles. Okay, so it's as simple as getting the dummy, setting its position. So set the position orientation, and then get the orientation. And this Euler angle, in fact, the Euler angle with respect to one of the coordinates will give me the pitch angle. And so I'll show you how that works. Okay, so this one I chose the homework problem. So I'm going to open the homework problem. And I'm not going to control the pitch of the torso, but I'm just going to show you how to set the gravity so that it always moves, whereas it's going downhill. And then I'll also show you how to get the pitch angle. Okay, so this is what I gave you for homework. And then if you run this, it basically stops. Okay, so what you can do here is, and I don't know if you've seen this, but if you click on module properties, okay, this thing shows up. There's something called dynamics. This is where you set the gravity. So let's just set it to 0. Okay, if you set it to 0, this is in free space. It's still moving, and that's because if you see this, I launched it with a certain speed of 10. Okay, so we can just kill that, just make it not move. So it's now not launched with the speed. Let's see what happens. So it's nothing is moving because clearly there's no gravity. Okay, now I'm going to first show you how to set the gravity programmatically using code. And then once you know how to set gravity, we can then set the gravity the way we want. Okay, so let's do that. So if you go to CoppeliaSim manual, so if you go here, there is something called array parameters. So just like we set int 32, float 32, there is something called array parameter. Okay, so we're going to set an array parameter. We need to look at, well, this is the syntax. I'm copying that. If you go to parameter identifiers, you see that there is. This is basically setting the gravity. So I need to set this particular variable in the format which I just copied. So let me do that first. So let me go here, paste that. Okay, it says number parameter table. So this is basically the number of the parameter. In this case, it's going to be that that particular identifier I just showed you. So we just need to take this, copy, set, okay, and then it needs to be the gravity. So in this case, I just want to use the gravity which I defined, which was there basically in the by default, right? Minus 9.81. So it's gx, gy, gz, and then if you run this now, it's going to move. Let's see. You see, it moved. That's because I set the gravity. Okay, so we got that, but now let's just try to set the gravity along the slope. So for that, I need the slope. So let's just call slope as 0.2. We need to have gravity. So let me define gravity as 9.81. And then if you want, you can have the direction. So we just had that formula. So direction equals, let's go counterclockwise, so +1. Okay, and I'm just going to copy paste that formula. So I set this up. Now let's just try to figure out what that yaw angle is, or the heading angle is. So the formula which I wrote down was, I get the XYZ position of the base, which is basically here happens to be the stand, and then I get the XYZ position of the torso. Okay, or it has to basically be the center. So do I have something for the center? I could use the motor. The torso is basically this whole thing. So if I use that, it's going to come with the middle. So let's just use the center of the motor. I think that will work equally well. So let's just do that. So I already have defined these handles. Torso, I don't have a handle for stand. Equals sim.get object handle stand. Okay, so what I need to do is let me just define an external function which sets gravity. That way it's much easier. I can just call it. So I'm going to define a new function, call it set gravity, and say end. And now let's just define. So I set it here to this value, and then if I need to call it, I just say set gravity. So it will call this function. Okay, now let's just set it the way we want to set it. So first let's calculate the XYZ position of the stand. So stand equals sim.get object position, and in this case it's going to be the stand position with respect to the wall frame, and then I should call it position stand. Okay, got that? Now I need to find the position of the center of the rimless wheel. So in this case I've just chose it to be the motor, or you could have a dummy there to give the position. Object position motor with respect to the wall frame. Okay, we got that. Now let's find the yaw angle. That's going to be math.a tan 2, and then I need to give, we can actually check the syntax of this. Lua math.a tan 2. There it is. So the a tan 2, the way it works is, if you want to find the inverse of x divided by a, then you give x comma y. In this case we want to find y divided by x, so I need to give it as y comma x. So let's give the y coordinate first. So that will be position motor, position motor. The y coordinate is, hold on, is 2 minus position stand 2. So that's the y coordinates of both of these, and then I need to have the x coordinate. So just copy paste the whole thing. Okay, and that should be y comma x, or tan inverse of y divided by x. And then I need to find the gravity now. So we have for gravity, just referring to the notes, gravity is given by gz equals gravity, which I wrote down as 9.81, so I just use that, times math dot cosine of slope. So that case takes care of the y z component. The gx is, if you look at the formula, it's going to be minus direction times gravity times math dot sine slope. So that gives me the component which I resolved along the horizontal, but then I need to also multiply it with the yaw angle. So math dot sine yaw. Okay, so that's the x component. The y component is similar. So copy paste, gy equals direction times gravity times math dot sine times cosine. So then now I need to finally just set gx, gy, and gz. Okay, so I need to set that up here. And one thing to remember is this is the initialization code. So it sets the gravity once, but we need to keep updating it every time step. So what I need to do is I need to copy paste it either here or the sensing code, whatever you like. If you like sensing, then let's put it in sensing. Okay, and see what happens. Oh, something really went wrong. Let's see what went wrong. Okay, let me know if you find anything suspicious. Gravity right, slope is right, direction is right. Get object position looks okay. Tx. Motor minus stand. Math.slope. We check these formulas.
Should there be a cosine for GY?
No, this is right. The sine slope is right.
Okay.
Right. The mistake is here. Gravity should be negative. Okay, I think this will take care of it. See. You can see it's moving in the counterclockwise direction. So just the gravity is missing. And this is going because there's a slope now, which is pointing towards that direction. Now, if you wanted to go counterclockwise, all you do is you go here and then change this direction. So now it's going clockwise. So it's really up to you. You've got to decide first which way you want gravity to point. Okay, so we'll stop here. This is getting gravity. Now let's talk about the next part, which is how do you figure out the angle made by this torso with respect to the vertical. Okay, and as I said, we've did two methods: spherical coordinates, which has its own problems because it does a problem with using a cosine. It basically gives you positive angles if the torso is forward or backwards, which is a problem with cosine because it's an even function. And the other method was to use the transformation matrices, which is a great idea, but requires a little bit of math. Now I'm going to show you a method which is probably which is more accurate, which is better than the spherical, is as accurate as the rotation matrix, but probably requires less computation than the rotation matrix. Okay, so here's how we do it. What we'll do is we'll add a dummy. Okay, and then you can not see it, but let me call that dummy frame, and I call it frame just because that dummy will actually keep moving with the object. So it's going to help me define a moving frame. So frame, and if you want to see it, I highly recommend doing this initially, is to change the size to maybe 0.1. And you don't see it because it's not in the view, but if you want to see it, the easiest thing I recommend doing is putting it as the child of, let's say, a motor, and then going to displacement, and then just saying that you want it to be same as the parent frame, because now it's going to be the same point as the torso. Okay, so it's over there, but what we're going to try to do is this. We're going to try to put it right below or at the projection of the hub, and then we'll keep moving it as this object moves. Okay, you need to manually tell it to move, but let's just put it right here below and you see what it looks like. So what I'm going to do is, the trick is here is, well, first let's remove it. We don't no longer want it to be a child of the motor. Open frame, and now go to the translation aspect of the frame, and then here instead of 0.5 just say 0. Escape to world frame. It's world frame, it should be 0. So now it's right below. Okay, so you got it down, and then if you let this go, that term is going nowhere because it's not associated with anything. But we will basically make it move manually. Okay, if you make it a parent and sorry, if you make it a child of something and move, then it's just going to mess up the frame. We just want it to keep it pure. We want to tweak its position and orientation so that it helps us to do what we are trying to do. Okay, so we define that. Let's just get handle sim.get object handle frame. Okay, now since we got the handle, we will manually set this to move with the object. So how we do that? Well, if you go to right here, let's say in actuation, so we say, so the way we want to move it is we want to keep it approximately below the motor, right? So let's just get the motor coordinates. I already have them over here, so if we just copy this. Okay, so that's the position of the motor, and so then we just set the position. So sim dot set object position, and then we want to set the object to be the frame, and I think the syntax is with respect to the world frame, so -1. And then I think you need to set what exactly you want to set. You want to send the position of the torso to whatever you want it to be. So in this case, it's going to be the x and y and the z coordinates. So now the x coordinate is going to be the same as the x coordinate of the motor. So I'm just going to copy paste this. The y coordinate is going to be the same as that of the motor, but the z coordinate is going to be 0 because it's going to be a projection. Okay, so if you keep this and now run it, you can see that the object is actually moving with the rimless wheel. Now what I also want to do is I also want to play with the orientation. I always want the orientation to be such that it is along the yaw angle. So what I do in this case is I need to get that yaw angle again. Now I'm just writing this all over again, but you can write the code more efficiently so that you don't compute the yaw angle twice. So I compute the yaw angle, but I need the stand stuff. So I get that. I get the yaw angle, and now what I need to do is, since this yaw angle is, if you saw my notes, the way the yaw angle is defined is, it's basically defined an angle made with the x-axis. So I need to rotate about the z-axis, right? That's all the rotations we've talked about in 2D is rotations about the z-axis. So what I do is I set the orientation. So sim set object orientation. In this case, the object is the frame. I want it with respect to the world frame, and then I need to give the Euler angles for that rotation. So the Euler angle, as said, is just one rotation about the z-axis. So 0 for x, 0 for y, and for z it's going to be yaw. Okay, and maybe I should just comment. Let me just comment this out first. Okay, and let's just look at these red, green, and blue arrows before I set the orientation. So okay, now you can see that they are still pointing in the same direction. Okay, a little bit more, and you can see that they're not changing. They're basically oriented in the same direction as these global XYZ. Now what I'm going to do is I'm going to change them to this orientation, okay, which is basically rotating the orientation too. See what happens. Okay, now you can see that they are actually not along the global XYZ. They're actually pointing this direction. So this is actually the orientation of the heading. Okay, and so the way it's shown this way is because in clockwise it's a little bit hard to think, because that angle is actually like close to 3.15, but if you do counterclockwise, you'll see that the angles are much more easier to imagine. So let's just run this, and you can see that it's actually rotating. Stop. Okay, so you saw it's green is still that way. Keep going. Anyway, so it keeps rotating and the orientation keeps changing. Okay, so we got that. We figured out the orientation we set the orientation to the dummy. The last step, which is probably the simplest one, is to actually get the torso orientation with respect to this dummy. So let's just do that. Okay, so for that, we need to use the command called sim.get object orientation. Okay, and then I need to specify, so it basically outputs the Euler angles. So let me just get the Euler angles, and then the inputs to the orientation are, which are also in the manual, are basically give the object about whose orientation you need to find, in this case the torso, and then you also give the frame about which you want to find it. So in this case it's the frame which is basically attached to the dummy and is moving with the dummy with the right orientation, right? You do that, and then we can say print Euler angles 1, Euler angles 2, Euler angles 3. Now if this works perfectly, then what you will see is that only one Euler angle will change, and that's because what's happening here is as this torso moves in a circle, its orientation only with respect to one coordinate axis is going to change. That's about the x-axis. Its orientation with respect to the other coordinate does not change. So another way of thinking of that is, if this rimless wheel is moving in a 2D plane. So if it is moving in a perfectly flat plane, not in circles, then you will see that only one angle changes, that is the pitch angle, but the other two angles, the three rotations associated with an object, the other two ones don't change. Okay, and so that's what you would see. So if we now run this, it actually prints the output here, and I can pause this. So you can see that this one is changing from 0, positive, and so on. This one is almost constant, the middle one, and the third one is also very close to 3.14. You can run this, keep running it, and you'll see that it changes. Only the first one. So you can see that wide excursion is probably somewhere here. See, 0.2, 0.27, minus 0.3. So it varies. So it's basically wobbling around passively, and that's why it's changing in a crazy manner. But then the other two angles are almost the same. Okay. Now what will happen is these are varying, but as you make the circumference of that circle longer and longer, so it's really short. If you make it longer and longer, you'll see that those angles will have lesser variability than they have over here. Okay, and so that's because we're trying to take an object which is three-dimensional, trying to make it 2D by using this boom, the spherical joint, and so it only has this effect of it's changing, varying the other two angles even though they should not vary. Okay, so that's it. So what do you do next is, once you have this Euler angle, you use the Euler angle. So the pitch angle is, you can say that the pitch print pitch equals Euler angles 1. That's all. Comment this out, and that is your angle for control. Okay, so once you have this, we can talk about more fancier animations now with two legs and so on. So I'll stop here.